This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your hosts, Radio Joe Hughes and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day wherever you're listening from, and welcome. It's episode 472 of IAQ Radio. It's Friday, August 11th, 2017, and this week we're going to flash back to a show we did with Mr. Jeffrey Siegel. This show wasn't too terribly long ago. Let's see, it was 2/27 of 2015, episode 358. Jeff was a great guest, good, solid research to practice information. The Z-Man and I are on our annual early August break, but we've gone through the archives to put together some great shows for you. We will be back live August 25th with Dr. Powell Wargocki. Don't miss that show. So before we get started, let's thank our marquee sponsors.
IAQ Radio marquee sponsors are John Don Products, where restoration and abatement contractors shop. Visit them at jondon.com. That's JONDON.com. Healthy Indoor Magazine, a free online digital magazine for industry professionals and consumers. Subscriptions are available at IAQ.net. Legends Environmental Insurance, the experts in insurance for environmental consultants and contractors for over 20 years at legends-enviro.com. That's legends-enviro.com.
Dr. Jeff Siegel is an associate professor in the Department of Civil Engineering at the University of Toronto. Prior to accepting his current position, he was an associate professor at the University of Texas, Austin. His interests and research have focused on healthy and sustainable buildings, ventilation and indoor air quality in residential and commercial buildings, control of indoor particulate matter, secondary impacts of control technologies and strategies, aerosol dynamics in indoor environments, and HVAC systems. He is also keenly interested in ensuring that good research works its way into practice, and this week we want to focus on that theme. Dr. Siegel's Ph.D. is in mechanical engineering from the University of California, Berkeley. He's also got a master's in mechanical engineering from the same institution, and his bachelor's is in engineering from Swarthmore College down in the Philadelphia area. He's a prolific researcher and speaker, very active member of the professional societies and associations, including the International Society for Indoor Air Quality and Climate and ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineers. Dr. Siegel, do we have you on the line?
You do, yep.
Great. Thanks for joining us. You're up in Canada now. You were in Pennsylvania, California, Texas. Where do you come from originally?
Well, I was born in Hamilton, Ontario, Canada, which is kind of the analog to Pittsburgh in Canada, a steel town. And when I was 13, we moved to Toronto, where I went to high school. And at some point after that, I went to Swarthmore College in Pennsylvania, found my way a bunch of different places that you mentioned already, including at the University of Texas at Austin, where I taught for about a decade. And then recently moved back here to Toronto in 2013, a couple of years ago.
So you're sort of back home up in the cold climate.
Yeah, this winter has been a killer, but yes, definitely back in Toronto. Glad to be here.
It's good, though, that you've had that kind of field experience, even if it's just in your own home in those different climates. You were in a cold climate, a very cold climate, a more western, probably a hot, dry climate, and then Texas. They've got 4 different climates down there, so you've had quite
all
a bit of
hot. Yeah.
all of them hot. Well, how did you get interested in indoor air quality?
So I started, I guess my first summer job after I started college was doing energy conservation research with an organization called the Grassroots Alliance for Solar Pennsylvania in Philadelphia. And that got me really interested in residential energy efficiency issues. And I did that for several years, some time after I graduated in Seattle with Ecotope Incorporated, and then continued that into graduate school. And then in graduate school, I took courses from Bill Nazaroff among others, and realized that indoor air quality was much neglected when compared to energy conservation. And so I started to get interested in issues that especially spanned both energy and indoor air quality issues, and got very much into indoor air quality, and I found a nice home in the field.
Do you see that changing at all? I mean, the emphasis has been energy efficiency, even more so recently because of the push to cut back on our energy. But do you see indoor air starting to open up a little bit?
I wish I could say yes, and I think there's been some nice public efforts. Every time I talk to people, just ordinary people, about indoor air quality, there's a lot of interest. It shows up in a lot of different ways in people's lives. But at the same time, when I look at things like research funding, when I look at national priorities in a lot of different countries, I still feel like we have, given its importance, we still have a lot more effort to get people motivated to pay as much attention to indoor air quality as they do to energy efficiency.
Yeah, the energy efficiency just seems to overwhelm, I guess. And we're going to talk more about this. People think of it as a pocketbook thing, and I don't think they realize how much they spend or what good indoor air quality costs and what the benefits are.
Yeah, no, I think that's exactly right. And I also think that there's a disconnect in terms of, in indoor air quality, not everything, but a lot of what we're dealing with are things that take a long time to see any benefit, or you're essentially avoiding problems a long time in the future. And that's a really hard thing to get people focused on, whereas you see a benefit of energy efficiency in your next utility bill.
Yeah, that's tough when you're looking at things like absenteeism or increased performance. They're tough to measure as well as you would like and as quickly as you would like. So I think it gets put in the back of people's minds. Cliff, let me turn it over to you.
Well, I'd like to talk a little bit about ozone if we could. Can you tell our listeners the basic science on ozone?
Yeah, and I mean, ozone is, of course, very complex. There are chemists who spend their whole careers studying some narrow portion of reactions that ozone occurs in. But practically, there are two or three things that are really important. The first is that ozone is really chemically reactive. It's a very good oxidizer, as you mentioned, and that means that certainly for certain kinds of compounds, ozone reacts with them very, very quickly. And it's a very important in indoor air because it's one of the most, if not the most prominent oxidizing agents in indoor air. So where I think things get a little bit confusing is that we all heard about the ozone layer and the hole in the ozone layer and the problem that caused. So people were assuming that ozone is a good thing. And the reason that ozone is good up high in the atmosphere, where it's blocking the reason that it's good is because it blocks ultraviolet light. And ozone is, in fact, very good at absorbing ultraviolet light, and that's one of the ways that we measure ozone in research instruments for measuring ozone concentration. So when there's a hole in the ozone layer, we get a lot of ultraviolet light through, which causes a whole host of environmental issues. However, when ozone is down near the ground, close to us, or especially in our buildings, in our homes, it reacts with a lot of common presence, certain kinds of fragrances, oils, including skin oil, a whole bunch of different things, and that might seem like a good thing because it's chemically breaking down some of those things. But the problem is not that it's breaking things down, but that it's sometimes forming things which are more harmful than the original items it's breaking down. So, for example, you can have a terpene, which is a chemical compound that might be associated with certain fragrances. So when you smell lemon or a pine scent. That's largely because of the terpenes that are present. When ozone reacts with those things, it can form a whole host of different things, formaldehyde, ultrafine particles, carboxylic acids, and the terpenes by themselves, not at all harmful until they get to amazingly high concentrations that you would never experience inside. But take some ozone, react it with low concentrations of terpenes, and all of a sudden you've got several compounds that we know are health risks. So that's the basic science, is that we worry about those secondary products from ozone. Now, I should also mention that ozone by itself is also a problem. Ozone reacts with the tissue in our lungs and causes a variety of respiratory effects, and it's in fact quite a serious pollutant, and it's regulated in outdoor air because of those serious health effects. So ozone by itself is a problem, and ozone reacting with things is a problem.
Based on what you said, are there any positive uses for ozone within indoor environments?
So I am of the opinion, based on everything that I've read and done over my career, that ozone should not be used in occupied environments. I have never once seen any data that is even suggestive that ozone has a health benefit to people. Everything I've seen suggests that ozone is negative. Now, having said that, there are some times in unoccupied environments where it might make sense to use ozone. An example is after a fire, there can be very strong odors, as you know, and that's one of the biggest remediation issues. And there are times where people use ozone, and it is very effective at reducing those odors. The comment I would make is that that's not all it's doing. It's reacting with everything else in the home and producing several things that are of concern from a health perspective. So it certainly shouldn't be used casually, but if it's being used by someone who's knowledgeable about ozone, who is removing, taking care to remove things that are going to be reactive beforehand, are taking care to clean up those byproducts after the fact, I think someone could probably make an argument that it has some utility. The other comment I would make about that is that ozone is also used for sterilization. So in fact, most indoor standards for ozone in the U.S. are based on the Food and Drug Administration standard, and that comes from the idea that ozone is used for sterilization. But you'll notice that when ozone is used for sterilization in a doctor's office or a surgical facility, the ozone isn't released to the room after sterilization. It's typically vented to the outside or otherwise controlled. So everyone acknowledges that ozone has some uses, but you really have to think about the negative consequences too.
Thank you, Joe.
And the reason we want to make sure we get the background information is that the next topic is these hydroxyls, and I'm not going to spend the whole show on this, folks, but we've been getting requests to talk about the hydroxyls, and Dr. Siegel agreed to kind of give us the basics on it, and then we'll do a further deep dive into it on a later show. So let's move on to the hydroxyl technology. Can you give us a little bit of a background on how that differs from ozone, how it's the same, and what your thoughts are on that technology?
Yeah, okay. So it gets very complicated here right from the outset because there is not a consistent terminology used by devices. So a lot of devices generate both ozone and hydroxyl radicals. A lot of devices generate hydroxyl radicals from ozone reactions. There's kind of a whole bunch of things here. But to say very shortly, hydroxyl radicals are very short-lived chemical species that, like ozone, engage in chemical reactions and can essentially break down or react with things that we might care about indoors, things that are producing odors or otherwise have contaminants. And I get pretty quickly out of my league in the chemistry here, but I will comment that there is a similar literature on hydroxyl radicals that suggests that you can have, hydroxyl-based devices that suggest you can have the same sorts of problems, the generation of unwanted byproducts by the use of these devices. So I am generally of the opinion that any air cleaning device that emits anything into indoor air, we should really think very carefully before we call it an air cleaning device. Because even if it has some positive benefits, the things that are emitted might also have negative benefits. And a classic example is devices that emit ozone or claim to emit hydroxyl radicals. The basic answer is I would personally never recommend one of those devices, and I would suggest others be very, very cautious on those sorts of devices, because the last thing we want to do is lead someone to believe that they're cleaning the air when in fact they may be degrading the air.
And I guess from what you said, we're really not always sure what they're producing. It doesn't seem to be consistent even between different machines for sure, but then even within the same machines, the same manufacturer model, you might get two different machines and get somewhat different results. Is that accurate to say?
Yeah, oh, definitely. I mean, we've tested many different types of air cleaners specifically for things like ozone emission, and you can find the exact same manufacturer, the exact same model of a device, and take two or three different ones, and they emit very different amounts, like factor of 2 different in how much ozone they emit, for example. So there's a lot of variation. And like I said, there's not a lot of consistency among these manufacturers in how they term their technologies. So even a device that emits ozone, sometimes that's called activated oxygen, sometimes it's called superoxygen, all kinds of different terms that kind of mask the fact that a device emits ozone. And so there's not a lot of standardization in how these devices are marketed. But that's not uncommon. We see that a lot in indoor air quality, where it's very hard for consumers to get good information. And
kind of going a little more into the air cleaner discussion, and that's something we wanted to really hit with you here today. You had another paper that I was reviewing, I don't remember which one, and you were talking about the secondary consequences from use of air cleaning devices. And it's not just that some of them may produce ozone, or can you talk a little bit more about that before we get more into the details on air cleaning?
Yeah, sure. So, I mean, I am of the opinion that when you're picking an air cleaner for a building, you have to really think about everything. So that air cleaner, you might be getting it to reduce particle concentrations, which is a very good thing to do and something I advocate doing in many, if not most, indoor environments. But a whole bunch of other things happen because you're using that air cleaner. That air cleaner is probably going to use some energy. So if it's a portable air cleaner, it usually takes some energy to run the device and or a fan in the device. If you're putting a filter in a central system of some kind, you're potentially are going to use more energy in that system because of the added pressure drop of that device. And so you have to consider the energy use. And we were talking a little bit before the show, and I think a point I would like to make more than any other point today is that, these energy consequences, we think about them a lot, and I am a big advocate for energy efficiency. So I think it's good we're thinking about energy. But the flip side is every time anyone does an analysis, the energy consequences of air cleaning are really small compared to the benefits that come from health, or that come from improved productivity, from the use of air cleaning devices. And so it's really hard to come up with an argument that suggests there isn't a net cost benefit from the use of good air cleaning devices. But the problem is, of course, it's like all economic arguments. It can be really complicated about who's actually paying the cost and who's reaping the benefits. And sometimes the benefits occur over a long period of time, so you don't see them for a long time, which is not usually the case with energy. So I'm not doubting that it's complicated, but I am saying that in general, I think it's good to think about energy, but the energy consequences of air cleaning are small. Now, another secondary consequence of air cleaning is really obvious when you think about it, but especially if you've ever changed the filter in your own house or in a building. The whole idea of an air cleaning device is to remove things from the air that we don't want to breathe. Well, those things that we're removing from the air are then sitting in the airstream that's going through the device. And so there's this possibility for kind of secondary contamination because we've removed the contaminants from the air in the room, but we're still blowing air across them. And, if you talk to old-time people who change filters for a living, who've been doing it for a long time, or maybe in your own house, that filters smell. They have an odor. And there's a lot of great research out there that shows that you can get ozone reacting with the particles on the filter. You can get all kinds of different emissions, formaldehyde, other things, from the filter itself or from the material that's deposited there. And so at this point, I think that, we're still accumulating data on some of these secondary consequences. Some of them are much clearer than others. But the general rules that I think about when I'm thinking about air cleaning devices is first the one I already mentioned. Anything that emits something into the air, I would have a lot of caution about its use. I would say the energy consequences are worth looking at, but chances are they're quite small in some buildings, and in some cases air cleaning can actually save energy costs in buildings. And then the third thing is the fact that air cleaners, a good air cleaner especially, is accumulating things we don't want to breathe, means that you should be paying attention to changing that filter or cleaning that air cleaner on the basis that the manufacturer recommends for the device. So simply having a good air cleaner isn't enough. You also have to maintain it.
I want to go into the filter forensics in a moment, but and that nicely led us into it, but you mentioned something I'd like to get you to elaborate on a little bit, and that is saving energy costs. How can putting a filter in, restricting airflow, save energy costs?
Yeah, it's about the most counterintuitive thing I can think of, especially when I first started looking at it. But here's what happens, and sometimes people don't believe this, and I suggest that they go out and measure it. And you can do this by putting a power meter on your furnace fan, for example. So if you increase the pressure drop, let's say you put in a higher pressure drop filter, because that filter is a more efficient filter. So it's higher pressure drop. What happens in not all residential systems, but really most residential systems, is that the fan sees that extra pressure drop, and it essentially slows down. It moves less air. And you can easily verify this yourself. I've done it lots of different ways, but even any kind of fan you have in your house, a box fan or anything else, if you block part of it, you move less air through the device. Well, if you have a power meter and put it on that fan, what you'll see is that when you move less air, the amount of electricity that the fan needs goes down too. And so I think where it gets counterintuitive is we think, well, that fan must be working harder. But it's in fact the opposite. It's working less hard. It's using less electricity. So right away, a bigger pressure drop filter will give you fan energy savings. They're not huge, a few percent usually, but nonetheless, it's not a consequence, not a negative energy consequence. Now, where it gets more complicated is, of course, that fan is not just serving to push air through the filter, it's also moving air through your central system to distribute your heating and cooling throughout your house. And when you slow down flow, a lot of devices, especially air conditioners and heat pumps, often get less efficient. So they have to run for longer to meet the same load. And so in some devices, you can find that putting a higher pressure drop filter can use a little bit more energy. But every study I've ever seen, I've ever done myself, I've ever been involved in, has all found the same thing. For residential systems, and we've also verified this for rooftop commercial systems, for any of these kind of smaller type systems, the energy consequences are really in the noise of the operation of the device. So putting even a very good filter in is going to have very small energy consequences and maybe even energy savings, but small is the important thing there. And what that means practically is that we are spending a little bit of money to buy a better air cleaning device, certainly. We're maybe spending a little bit of energy, maybe saving a little bit of money on energy, and we're getting all the benefits of improved air quality. So like I said, I think the energy issue is worth talking about. It's worth focusing on. I'm glad people are thinking about it. But the flip side of it is I've never seen a scenario in a smaller building where, it's even worth worrying about the energy consequences of air cleaning. Much better to just do the air cleaning, get the benefits from it, and the energy consequences are often small.
Now, I guess you would also caution against going too far in increasing the resistance. I mean, could it not cause a problem with the motor, the blower, cause a little strain?
Yeah, I mean, I'm actually most worried about air conditioning systems, because when the flow gets too low, you run into the scenario where you get ice build up on the coil, and anyone who's been around enough residential HVAC systems knows that there are some systems that, for whatever reason, it might be the filter, but more commonly it's a duct design problem, don't have enough flow at their cooling coil, and it turns into a block of ice. So it's not a very good air conditioner at that point, and all the energy you're putting into it is essentially wasted, and you can run into some damage. So sure, I would agree that you don't want to put a 3-foot thick HEPA filter in a residential system because the fan won't move any air through it. But the flip side of that is I think we have a much bigger problem that extends beyond indoor air quality, that we're not paying enough attention to our residential HVAC systems in general. And so, if you look at the big studies that have been done by people like John Proctor in the southwestern U.S. and other places, a lot of systems don't have enough airflow. Forgetting about the filter, just their design is poor, so they don't have enough airflow. A lot of systems have way too much refrigerant charge or way too little refrigerant charge, which has a whole host of energy issues. And so I would say that, sure, you should be careful, but the flip side is we've got a lot of problems out there, and we could get enormous value as a society on both an energy and an indoor air quality if we put a little bit more attention in our design, operation, and maintenance of our residential systems.
Before we go to our halftime, we're real close now. I think we probably should, but before we do, I'd like you to just kind of prep people for the second half here and give us a little overview of what you mean by filter forensics, what you're doing with filter forensics.
Sure. So the whole idea of filter forensics is, we have these filters in central systems throughout many buildings in the U.S. and Canada and throughout the world. And those filters, we think of them as a waste product. They collect stuff from the air that we don't want to breathe at the end of their service life, or often much after the end of their service life. We get around to changing them and we throw them in the garbage. Well, I think that those filters are actually a valuable resource because they're collecting particles from the air. And so we can use them to actually look at what people in the house were exposed to. And they offer a whole lot of advantages because they collect a lot of stuff. If you've changed the filter, you know how dirty they get. And they're collecting material from all over the building, and they're concentrating it in one location. And it's a lot of material that gives us a lot of opportunity to analyze it and understand what people in the building were exposed to.
And what we'll do is, after we come back from thanking our sponsors, we'll talk a little bit more about what type of research you've been doing with respect to this filter forensics and what you're finding and how that applies to our indoor air quality consultants and contractors out there. So we'll be right back with Dr. Jeff Siegel. Got to stop and thank our sponsors. Give us about 90 seconds.
IAQ Radio would like to thank our association sponsors. The Indoor Air Quality Association, a nonprofit multidisciplinary organization dedicated to promoting the exchange of indoor environmental information through education and research. Visit them at iaqa.org. Particles Plus, engineers and manufacturers, feature rich particle counters, air quality monitoring, instrumentation, and vacuum pump technology. ParticlesPlus.com. Count on us. Gray Wolf Sensing Solutions, who use advanced sensor software technology and embedded computers to provide superior environmental test instrumentation. Visit them, wolfsense.com. IAQ marquee sponsors are John Donn Products, where restoration and abatement contractors shop. Visit them at johndonn.com. That's JONDON.com. Healthy Indoor Magazine, a free online digital magazine for industry professionals and consumers. Subscriptions are available at IAQ.net. Legends Environmental Insurance, the experts in insurance for environmental consultants and contractors for over 20 years at legends-enviro.com. That's legends-enviro.com.
All right, we're back for the second half of our interview. We've got Dr. Jeff Siegel calling in from the University of Toronto. We were talking a little bit about filter forensics before the break. I just kind of wanted to introduce the subject, and I'd like, if you would, to kind of give the listeners an idea of what type of work you've been doing with respect to this filter forensics. Are you doing it in residential, commercial? What are you looking at? What are you finding?
Okay, so I want to start by saying that when a colleague, Kerry Kinney at the University of Texas, and I first started talking about this idea maybe 2008 or so, we thought we were really onto something really interesting and really new. And then, of course, you start reading articles, and some other people in the literature had done a similar thing. And then a researcher named Jim Hanley at RTI showed me an article from 1950 where some researchers had used filter forensics, looked at the dust collected on filters and outdoor air intakes to look at outdoor air quality. And then I started talking to a bunch of industrial hygienists, and people have been using filter forensics for a very long time. And how it's typically been used historically is a lot of times in an infectious disease context. So people get sick in a building, and an industrial hygienist collects the filters from that building and cultures the microorganisms on that filter and tries to find the agent that's making people sick. And so that's, really the history of it. And how we've used it is in a variety of different ways. Mostly it's been in residential buildings, although we have done some work in big box retail stores with the approach. And basically, it's as simple as it sounds. We collect the filters from a building, and we analyze the dust that collects on those filters. And so far, we've done analysis for many different kinds of microorganisms using both DNA-based techniques, which are kind of the newer thing, as well as culture-based techniques. We've also looked at heavy metals. We've looked at semi-volatile organic compounds. We have a project now, that's things like plasticizers, phthalates, things like that. We've got a project now where we're looking at allergens and asthma triggers in dust from filters from homes. And so you can really look for anything that's bound to particles. And it's a way of saying, well, this filter's been in place for a month. That's typically how long we use it for. It's sampling air from the entire volume of the building. And a lot of air flows through a filter. So it's what we call in the science world a large volume sampler. And it's got this huge collection of material on it that's a really rich resource for us in terms of understanding the indoor environment.
So what kind of things have stood out when you do this analysis?
Well, so many. A couple of examples. Federico Norris, who is a graduate student, co-advised by Kerry Kinney and I at the University of Texas, he did some early work with heavy metals, and including, for example, lead. And, most people think that lead is kind of a non-issue from an airborne perspective. Because we don't use lead in gasoline anymore, we don't use lead paint anymore. But what we found in a sample of homes is we could tell the age of the home by the amount of lead we found in the filter. So that is to say, an older home that was built before lead paint was banned would have a higher lead signature in the filter. So we could tell that. We were also looking in that same study at cadmium, which is a constituent of cigarette smoke. It's getting harder and harder to find smokers, but we had one house in the study that had smokers, and that was the only house that had a big signature of cadmium in the dust in the filter. And so those are a couple of examples. We also see, for example, when we will talk about the microbiology, we see a big difference between a house that's densely occupied, got a bunch of graduate students living in a house, versus a house with just a couple of people living in it. We see different microorganisms associated with human density. And we see other impacts. For example, the fungi. We can look at the fungi on a filter, and most fungi ultimately come from outdoors. And so we can see differences. So, for example, we had big box retail stores in Pennsylvania and Texas, and they had completely different fungal communities on the filter because there are completely different fungi in Pennsylvania and Texas. And so you can really tell a lot about a building just simply by looking at the dust that collects on the filter.
Cliff, I just want to make sure if you had anything, you got a chance to jump in.
I'm good, Joe.
All right, let me follow up a little more on that subject. With respect to practitioners out in the field, how would you? I mean, I know I've done some filter testing before just to look for things like asbestos. This was many years ago, and then I'm wondering, what would you recommend for practitioners out in the field? How useful would this be for someone doing an evaluation of an indoor environment? How would they go about determining? There's so many things to look for, I guess. How would they go about making this practical for them in the field?
Yeah, so I want to be clear. I'm a researcher. I'm an academic. So this is something that we're working on. But let me tell you what the vision of this is. So I see lots of places where it would have practically a lot of utility. So let's say you've got a scenario where you have some type of wildfire or industrial accident or something else that causes a plume of particles of a certain kind. Often, you evacuate people in the immediate vicinity of the event. But then there's a bunch of people who are kind of outside the immediate vicinity, and we usually tell them to shelter in place. Go inside your home, close your doors and windows, run your central system if you have one, and kind of protect yourself from that outdoor air that's got contaminants in it. We don't really know how much those people are actually exposed to things because we focus so much on outdoor air and not enough on indoor air. So as an example, let's say we have another event like the Fukushima Daiichi nuclear meltdown. We could collect filters from people's houses and look at how much exposure, something like radioactive compounds. It's a very quick test to determine how much radiation they were exposed to, and then that could lead to medical decisions. So I can think of a lot of kind of what I call extraordinary events where we could use filter forensics practically as a way of saying, okay, who do we need to get treatment to the fastest? But a little bit more practically, the sky is the limit in terms of what we can look for in terms of compounds. But some things are really expensive and really hard to look for, and some things are really cheap and relatively easy to see. So, for example, a lead test on dust from a filter is a few dollars. Doesn't require much processing of the dust, very easy to do. Well, maybe we see that lead correlates with something else that we're interested in. And so we can then say, oh, okay, so we can look for what are the cheap indicator pollutants for things that we care about, as well as they might be telling us something about other exposures. So we can kind of start looking at, can we use this, can we kind of cherry pick what we're looking for because it's cheap or easy to see, and have that tell us a little bit more about the indoor air quality in a building. And then the third way, where I think this is one day going to be useful to practitioners, is right now, the people out there who study indoor air quality for a living know that a lot of instrumentation is very, very expensive for looking at indoor air quality. And not only that, you get a snapshot of what happens when you happen to be there monitoring. And so what filter forensics offers is an time-integrated history of exposure. And so instead of that monitoring resources, especially if you combine filter forensics with characterizing the HVAC system that the filter comes from, so knowing the flow rate going through it, know how often the system runs, then you can start backing out actual air concentrations of contaminants. And instead of doing that very expensive snapshot monitoring that might not be relevant to actual exposures that happened before, one day we can use the filter to tell us something about what people were exposed to and make indoor air quality decisions that are based on not just an instant in time when we happen to be there measuring, but the real integrated exposure that's kind of more meaningful from a health perspective.
I think people try to do that somewhat now with dust in homes, and they look at that as more of a longer term type exposure. But I can see how the dust that gets through the mechanical system is dust that was more likely to be inhaled or a higher level of exposure in many cases. What about the level of filtration that you use? Is there a specific MERV level that works better than another, or have you found that not to be the case?
Yeah, it turns out that, again, if you've ever changed filters, you know that they get dirty. They get dirty pretty fast. So we've tried all different efficiencies of filters, everything from very low efficiency, kind of MERV 2, 3, essentially what we usually call boulder catchers, the really coarse fiberglass filters, up to as high as MERV 12 or even a little bit higher, which are much, much better filters. And what we've found is that the kind of a nice balance is somewhere around a MERV 7 or 8. So, a decent filter, but not a great filter, is what works well for filter forensics. And the idea here is that an important thing is to capture a lot of particles, and a MERV 7 or so filter is adequate for that purpose. And then also, on the kind of practical side of things, you want a filter that's easy to get the dust off. If you have a really deep filter that's got a really complicated surface that the particles kind of get embedded into, it's really hard to get them off. And then one of the big issues we face in filter forensics is with that extraction of the dust from the filter. So if we can have a filter media that's easy to extract, that works well for us. And we've been using, like I said, for almost all the research we've done with filter forensics, we settled on somewhere in the neighborhood of MERV 7 or 8.
And what about for volatiles, VOCs? Have you done anything with activated carbon or other types of filters?
So certainly from a practical standpoint, you had Richard Corsi and Josh Aldred on the show, and they talked a little bit about activated carbon for ozone removal. From a filter forensics purpose, we're still working on some ways of looking at things like volatile compounds or things that are short-lived. And I think the direction we're going to go in, and this is very kind of blue sky, something hopefully we'll get to much later in time, is you have to find some way of stabilizing those things on the filter, because obviously something like a gas molecule will probably go right through an ordinary particle filter, and you'll never know if it was there or not. But if we could have a way of capturing that in such a way that it could be recovered later, then we could start using filter forensics for looking at other things besides things that are associated with particles. And we'll get there one day. We're not there now.
Okay, well, that's an interesting subject. I'd like to move forward. And Cliff, unless you have anything else on the filter side, I think he probably got your interest when we talked about wildfires there for a moment. I wanted to make sure you had a chance to follow up.
Yeah, no, I'm okay, Joe.
Okay, because Cliff's a big restoration guy, and I think thinking about you mentioning wildfires, that seems like another area that would be promising for the future to look at exposure from filters. All right, let's move on to the microbiome of the built environment. I got a paper here that I was looking at, and I see that you had 4 different methods now for measuring I guess it would be microbiological organisms or biological organisms. You were talking about culture, qualitative polymerase chain reaction, Qpcr. I think most of our listeners are familiar with those. And then you had Sanger sequencing and pyrosequencing. I'm wondering if you could maybe expand on what those are a little more for our listeners and how close they are. Are they ready for prime time?
Sure. So I want to preface what I'm going to say with a few words here. I think that, from an indoor air quality perspective, the microbiome of the indoor environment is really interesting because it's so unexplored. We're just surrounded by microorganisms. Our bodies have, many more bacterial cells than we even have human cells. We're just essentially walking hosts for our microorganisms, and they're on every surface indoors. They're everywhere. And, a lot of people think that, that's kind of gross or something like that, but I'm more of the opinion it just is, and it's really interesting from the perspective is those microorganisms probably affect a lot of our exposures to pollutants. Those microorganisms in some cases are probably helping us in terms of health. In other cases, they're protecting us. In other cases, they might be hurting us. If you think about something that's pathogenic or causing an infectious disease. So it's this really interesting area, and so we want to have a way of understanding microorganisms inside. And the way we've generally all done it historically is with something called culturing. And, this is a time-honored tradition. It's been done for hundreds of years. And the idea is basically you take a sample, might be an air sample, might be something else, you put it onto some kind of growth media, and then you count and identify the microorganisms that grow on that growth media. Now, the problem with that is that some microorganisms are really culturable, and some aren't. And so, in fact, most indoors aren't. The data from microbiologists is something like about in the neighborhood of 0.1% or maybe even less of the microorganisms indoors are things that culture well. So we're missing most of what's out there simply by using culturing. And so that led, or that didn't lead to, but one of the effects of the revolutions in DNA sequencing, and everyone's familiar with things like the Human Genome Project and everything else, that now we start looking at the DNA that's there, and other methods of sequencing like Sanger sequencing or pyrosequencing, or these days people use something called Illumina sequencing. It changes very fast. And what those do is those look at the actual DNA that's there. It's an amazing process chemically and biologically. And they see all the DNA that's there, and then you look at a big library and say, okay, I found this chain of DNA. That means that it's likely to be this microorganism. So from a practical indoor air quality perspective, the really interesting thing here is that we have this great new tool for seeing what's indoors. But there's a flip side to that great tool, and that is that we haven't really done a lot to say, is this at all relevant for people's health indoors? And one of the kind of both challenges and opportunities with these new techniques is that they give us an amazing amount of information. You get hundreds of gigabytes of data from a single sample of all those DNA sequences. So it becomes this huge bioinformatics problem to actually see what's there. And then you see what's there, and unlike culturing, it's not really quantitative in a couple of different ways. So one way it's not quantitative is because it doesn't really tell you how much of the different microorganisms are there. So you might see, oh, I've got this dangerous pathogenic microorganism inside, some kind of toxic fungi, which is pretty rare. But you might have 1 in 10 billion of the microorganisms you found was that microorganism, and it's of no consequence at all to anyone's health. And so these modern techniques tell us a lot about the community of who's there, but they don't tell us very much about how much is there. And so you mentioned Qpcr. Qpcr does tell us how much of microorganisms are there. But the problem with Qpcr is that you have to know what you're looking for before you look for it, because you use certain chemicals called primers, and the primers are all specific to certain organisms. So if you don't use the right primers to look for the microorganism, you're not going to find it, not because it's not there, but because you don't have a primer that would let you see it if it was there. And so the way that, and there's a lot of really great people on both the microbial ecology side and the microbiology side, as well as on the building science side, that are trying to make some of these DNA techniques more relevant, and starting to see some really interesting findings. But I think that the big message that I think we should all get is that our future is going to be in some of these DNA-based techniques, no doubt about it. But the flip side of it is I don't think we're quite there yet from a practical purpose. There are some narrow purposes where I think a Qpcr analysis might make some sense if you're trying to tell the difference over time or something of a given environment. But I would say it's much more useful right now as a research tool than as a practical tool.
And what about these other sequencing techniques? How are we coming along with those?
Yeah, I mean, it's interesting. I'm not a microbiologist, and when we first started doing this, my first interaction with microorganisms was in about 2008 or 2009. We used something called Sanger sequencing, which really is a ton of work. It took the graduate student, Federico Norris, who did that. Essentially, it took him about a year of really a lot of effort just to get the technique working where he could get useful DNA out of samples we had taken from filters. So, and by the time we were publishing the data on that, which was maybe 2010 or 2011, nobody used Sanger sequencing anymore in the biology community. They had all moved on to something called pyrosequencing. Pyrosequencing was much easier to do, still hard, but much easier to do than Sanger sequencing, but it gave a lot less specific information about the microorganisms, but told a lot more about the overall community. So, so people use pyrosequencing, and then within a year and a half, the technology changed again. And now people, I mentioned, use something called Illumina sequencing or something like it, which again, we've moved in the direction of providing a lot more information about the community, but a lot less information about specific organisms. So we're kind of moving in a direction from a practical purpose of something that's, I think, really beneficial to the microbiological community, but maybe a little bit less practical for the indoor air community. And I almost think we need, as an indoor air quality community, to kind of rethink some of these things. And, there's a lot of instances, I think, where culturing is probably the right approach. It might not tell you about very much in the indoor environment, but if all you care about is if it tells you the things that are important to you in that indoor environment. And so I would hope that the indoor air quality community doesn't kind of jump on the bandwagon of these new techniques and instead says, okay, what's appropriate for our purposes? And what we need to achieve that is, good collaborations between IAQ practitioners, building science researchers, and microbiologists and microbial ecologists. And, we're starting to see some of those collaborations. I have many great collaborators in the microbiology world, and we're starting to see those partnerships kind of come to fruition. But I think that the practical message that's really important here is that I have no doubt that microorganisms are really important to the indoor environment and to indoor air quality. Where I have a lot of questions is exactly how they are. Do we want to encourage microorganisms inside? Do we want to discourage them? Do we want a really diverse microbial community with a lot of different microorganisms, which there's some evidence in the literature for that? Or do we want to try and target and get rid of the bad, or not the bad, but the pathogenic or problematic microorganisms? And that's I hate to be the researcher saying, we need to do more research, but that's essentially what I'm doing. I think we'll get there. And I can envision a time in my lifetime where we're designing buildings to have healthy microbial communities inside. So we're doing some kind of monitoring over time. We're looking at events that make the microbial community maybe become less diverse or more likely to have pathogenic or otherwise problematic microorganisms. And, maybe we'll eventually get to the place where we can steer that ship. But my personal opinion is that we're pretty far away from that right now.
Well, with respect to what we have now, or what you see is kind of maybe right around the corner, what are some of the emerging IAQ issues that practitioners should be aware of?
Okay, so one of the big ones, and I know there's lots of practitioners really engaged in this issue, but one that I think we need as a community to devote a little bit more time and energy towards is the whole issue of moisture indoors. If I had a nickel for every time I'm talking to someone about indoor air quality, and they think that mold is a problem, that's not necessarily the true. There might be an issue with mold odors. There are certainly some molds that are a problem. But a lot of cases, mold is actually an indicator for the underlying moisture problem. And so I would say as a community, getting people to understand that moisture problems are a real issue. When I drop my daughter off at school, I look up at the ceiling and there are, stained ceiling tiles. Those white, those brown stains on the white ceiling tiles that everyone's familiar with. To me, that's a really big indoor air quality concern because there's lots of great research by Mark Mendel and others that show that when there are moisture problems, we see a variety of health effects, especially for respiratorily compromised individuals. So I think we've got a public education piece of getting people to think much more about moisture problems. And then we've also got a practical piece of, going back to basic building science and realizing that, you can't have a sustainable, healthy building if you haven't done all the things you're supposed to do in terms of managing moisture. So I don't know that that's an emerging issue because we've had water causing problems in buildings since as long as we've had buildings. But at the same time, I think that we have a lot of opportunity for making that much more central to indoor air quality.
I think that's interesting.
A second emerging issue. Oh, go ahead.
Well, I just think it's interesting you chose that because, and it makes me think. A lot of times we think about, okay, what's next? A lot of people feel like we understand water damage and mold and microbial, but I think it's interesting you feel like we still have a long way to go there, and there should still be a really strong focus in that area. I like that. But go ahead, you were going to mention a second area.
Yeah. So a second area is what I would kind of classify generally as emerging contaminants. And so there's a lot of things that we only realize they're a problem when we start studying them. So if you think about particulate matter, 20, 30 years ago when we started realizing some of the health hazards of particulate matter, it focused on PM10, particles 10 microns and smaller. Then, subsequent to that, we realized that a lot of the health effects were associated with PM2.5, or particles smaller than 2.5 microns in diameter. And we haven't quite got there from a regulatory perspective, but I expect that within a decade or so, we'll be talking a lot about ultrafine particles, or particles that are smaller than 0.1 microns in diameter. Now, what's interesting to me is that, regulation always lags behind the science because you need to do the science to understand, to have good regulation. And there's a pretty high bar for having science integrated into regulation. But I do think that we really should be, as people who care about indoor air quality, we really should be thinking about ultrafine particles more. Another class of emerging contaminants, and if you haven't already, I hope you have someone on your show who can address them directly, are semi-volatile compounds. And those are things like plasticizers, which have received a fair amount of attention, especially in Europe, and now flame retardants. And I think that the stories that we have with flame retardants are very familiar to people who've studied environmental pollution for a while. We used one type of flame retardants. We realized it was an issue. I mean, I remember as a kid growing up sometime in the mid-'70s, and my mom took away most of the pajamas that I had because they had tris in them, which was identified as a flame retardant that causes health effects. And, we keep moving to new flame retardants as we find out health effects of existing flame retardants, and we're essentially doing a big uncontrolled experiment with flame retardants. And I think that as IAQ practitioners, that's something that should really be focused on is to start looking more at flame retardants as a potential health effect or as a potential cause of health effects. And I have to say that I kind of believe very strongly in the precautionary principle, and that is to say if there is something that we think might be causing harm, I think we should be careful, but we should try and limit exposures, even maybe before the science is fully there. And so we have to do that carefully because we don't want kind of bad science to be influencing what we do or inadequate science. But at the same time, I think that as practitioners, it's really important to stay up on some of this evidence because, it does change pretty quickly what we care about. And I'll give you a very practical example now. One of the ways that we can achieve energy efficiency in a building is by using spray foam. Now, spray foam is a wonderful product. If you're someone trying to renovate, make an older building more energy efficient, it's pretty hard to do it without spray foam. And it provides insulation. It can stop unintentional airflows. Really solid product from an energy perspective. Well, a lot of spray foams are about 30% by weight flame retardant. And, they're using some different flame retardants that we don't really have good toxicological data on yet. But I do think that this idea of, well, let's make this house energy efficient, let's use lots and lots of spray foam, and then not also think about the potential indoor air quality consequences is not the right way to do things. So instead, why don't we assume that there's a risk from the flame retardant in spray foams, and why don't we manage that risk? So, for instance, why don't we put the house under positive pressure for a period of time after it's built to when the off-gassing is greatest of those flame retardants? Why don't we be really meticulous about cleaning up all the construction dust, little pieces of spray foam? Why don't we follow good practices? Because there's, emerging evidence of a health effect, and the worst that happens is that we are overly cautious. And the best that happens is that we've actually protected people from a serious health risk. So those are a couple of examples of what I see as emerging contaminants.
Well, I appreciate that. We appreciate you joining us. We run a little bit over, but we can do that, and we really. It's been fascinating. I've enjoyed it, and I look forward to. We're trying to work out to have you come and speak at our conference in Seven Springs at the end of September, beginning of October. I think most listeners are somewhat familiar with that. Cliff, before we go, is there anything you wanted to ask?
I just wanted to thank Jeff. My right arm's tired. I can't remember when I wrote as many notes.
Cliff's writing his blog. It will be a long one this week, and we'll send that to you to review before we send it out. I just wanted to ask you, is there anything that we missed that you'd like to add? I know we scratched the surface of so much information that you have. I went through your CV here and was like, wow, I want to ask about this and this and this, but we've only got an hour. Is there anything in particular we missed that you'd like to add?
No, there's nothing that was missed. The one comment I'd like to make is that, I believe that one of our biggest challenges in indoor air quality from both a research perspective and a practical perspective is the public education piece. And I think where people like me can do a much better job is in getting the word out about indoor air quality. And so I think conversations like this, I really enjoyed it, but I also think they serve a really important value in terms of getting people kind of interested, motivated in indoor air quality. And I hope that everyone on the practitioner side, on the researcher side, can keep getting the message out there. And I think the more we do that, the more we'll be successful in improving indoor air quality.
Well, thank you for that, and we're going to keep trying here, and I know you'll do your best, and we look forward to talking more and getting together hopefully here in the fall. I want to thank Dr. Jeff Siegel for joining us. It was a great show. I really enjoyed that. A couple things that went different direction than what I expected, and that's always fun. I also want to thank the Z-Man, my co-host, Cliff. Great job. Interesting blog, I'm sure, this week.
Will be.
Of my engineer here, John. Yeah, you got to have faith. We had one minor glitch, but he figured it out, Cliff, at the very beginning there. Sometimes our TalkShoe connection just kind of drops on us. But anyway, it all went well. I also want to thank all of our listeners. I see a few regular names up there on the chat board. Please come back. I'm trying to get another gentleman from Toronto who has been on the show in the past, Dr. James Scott. I'm hoping we're going to be able to nail him down for next week. He's a fascinating guy. We'll continue the discussion of the microbiome. But anyway, we'll be back here next Friday at noon with the next broadcast of IAQ Radio.
For IAQ Radio, I'm Spike Reel saying thanks for listening.